Wind is chaotic, invisible, and incredibly powerful. To measure that raw physical energy, we have to capture it with dedicated hardware. In this guide, we are going to wire a physical anemometer and a wind vane directly to a Raspberry Pi and write the Python code to translate those physical movements into real-time wind data. To follow along, you will need your Raspberry Pi, the two wind sensors, an MCP 3008 analog-to-digital converter, a breadboard, and a 4.7K resistor. Integrating these two specific sensors transforms a general-purpose computer into a specialized tool for monitoring and recording precise local weather patterns. Step 1 is capturing the wind's speed. Take the two wires from your anemometer. Connect one to any ground pin on your Raspberry Pi and connect the other to GPIO 5. This diagram shows the anemometer's internal mechanics. A small magnet rotates on a central axis. Every time it passes a reed switch, it closes an electrical connection. That tap registers as a 1, a digital pulse, sending an on signal straight to the Pi's GPIO pin. Because this acts exactly like a physical button being pressed, we can write a short Python script using the GPIO 0 button library to detect those exact signals. Now, run your script and manually spin the anemometer cups to verify the wiring. You should see your Python console print a confirmation message every time the cups complete a full rotation and trigger the switch. While counting digital pulses confirms our hardware works, a raw pulse count is only useful once we apply the mathematics of speed. This formula breaks down exactly how we calculate speed. We start with the basic rule. Speed equals distance divided by time. To find the distance the cups traveled, we multiply total rotations by the circumference. We find the circumference by measuring the sensor's radius and multiplying by 2 pi. We also divide our recorded signals by 2 because the reed switch triggers twice for every full rotation. Next, we multiply the result by 1.18. This anemometer factor accounts for physical friction and wind energy lost as the arms turn. Finally, we convert our output from centimeters per second into kilometers per hour. Update your Python code with this math, run the script, and spin the device again. The console will now output actual speed values. Integrating these specific mathematical adjustments provides a method for aligning your custom DIY hardware with professional, standardized measurements. Now we look at the wind vane, which dictates direction. This schematic shows the vane houses an 8-point wheel of resistors, each with a different ohm value mapping to a specific compass direction. Because the vane's rotation changes the resistance, it outputs a smooth, continuous analog voltage wave, but the Raspberry Pi can only understand binary digital signals. To bridge this gap, we insert an MCP 3008 analog-to-digital converter chip and a 4.7K ohm voltage divider. This hardware translates smooth analog variations into discrete digital blocks the Pi can process. Wire the converter chip's SPI pins directly to the matching SPI pins on your Raspberry Pi, and connect the output of the wind vane to channel 0 on the chip. Before you test this, you must open your Raspberry Pi preferences and manually enable the SPI interface. If you skip this step, the board will fail to communicate with the chip. With SPI enabled, write a script to read channel 0 and slowly turn the wind vane. You will see the console report fluctuating numbers between 0 and 3.3 volts. The MCP 3008 provides the standard interface needed to read data from a wide variety of analog sensors beyond just wind direction. So, we have our raw voltage numbers, but we need to map those specific voltages to human-readable compass angles in our code. This Python interface shows the solution. We create a dictionary where each specific voltage reading from the sensor acts as a key that maps directly to an exact degree value, like 0.4 volts equaling 0 degrees. Because analog voltages naturally fluctuate, your live readings will rarely be perfect. You must round your incoming voltage data to 1 decimal place so it matches the exact keys in your dictionary. This deliberate data cleaning ensures that erratic analog hardware functions reliably within a digital environment. Now take your speed calculation loop and your wind direction mapping script and combine them into a single unified Python program. To verify the final build, spin both sensors by hand. The console will immediately report a clean, perfectly formatted stream of real-time wind speed and direction data. You have successfully captured digital pulses, applied friction-compensating mathematical formulas, and executed SPI conversions to decode analog voltage. Your live data collection system is completely operational. In the next video, we will take this telemetry stream and route it into a MariaDB SQL database, allowing you to record and archive your local weather data